All right, section 3.5, limits at infinity. All right, we're going to be taking a look at what happens as we go to the ends of our graph on the x-axis. Our limit, as we're looking at this, is going to equal a constant number. That doesn't always happen with graphs, but the ones that we're looking at in this section are going to have that feature. And we're going to take a look at a graph. So take a look first at the statements that are listed here. They talk about what happens as you go towards x equals infinity. That's the first equation, or the first statement. And then as x approaches negative infinity on the second statement. And what they're saying, let's draw a picture to correspond with this. I need more space on this screen, by the way. And we're going to draw a graph that you're familiar with. So this is a graph of 1 over x. And what this is saying is that for every epsilon greater than 0, there exists an m greater than 0, so that when f of x minus L is less than epsilon, that will happen whenever x is greater than m. So let's get our pieces on here in the right order this time. Here's my m, and over here is my n with this definition. Thank you. So if my x value exceeds m over here, right, or eventually my x value will exceed m, when the distance between L, so this is approaching, in this case it's L equals 0, right? It's leveling off at the x-axis, so L is equal to 0. Eventually the graph will be closer to the x-axis than the epsilon away. So this piece right here, I didn't label it last time, and this is epsilon. I need a smaller pen. Let me do that. Okay, so here's epsilon. So the epsilon right here is this distance away, right? And that within that distance, if I go out far enough, there's another x value that will actually be lower than epsilon, and it will be further out than m. And I can do the same picture over here. Eventually, there's an x over here that does the same sort of thing. It gets closer to the x-axis than I was before at the m value. Okay. This then is talking about the value that it's actually equal to. This is happening as a horizontal asymptote. So when this happens, when this limiting process happens, we get a horizontal asymptote. All right. Now we're ready, right? Much better. If R is a positive rational number and C is any real number, then the limit as x approaches infinity of c over x to the r is 0. That should kind of make sense. If I take values that are getting infinitely large and I raise them to power, a power, you have to pick a power for it to work, right? So r is a constant number. And we let the value go infinitely large. So let me give you an example. So if I let x increase by tens, I'll just draw a table real quick to justify what's happening here. So my x value, it goes from 10, and then it gets bigger, and it's at 100, and then it's at 1,000, and then it keeps going, right? So powers of 10. And we put this in here, and I need my r to be something, so let's just let r equal to 2. It doesn't matter what it is. So then I have 1 over 10 squared, and then I have 1 over 100 squared, and then I have 1 over 1,000 squared. Get all those zeros in there. All of these are getting infinitely large in the denominator, right? The overall fraction's getting infinitely small. And we saw this kind of a feature happening from a different perspective. This actually would tend to 0. We did that back in chapter 2, that sort of perspective. But this is a very specific kind of function. These are rational functions of the variety that it's a constant on top, specifically a 1 here, but it could really be any constant. Or it does, my example was a 1 on top. Theirs says any constant on top, and I'm dividing by a power of x. And the x values are getting infinitely large. So when that happens, I have my limit is 0, and it works for both positive values and negative values. So while I used 10, 100, 1,000, I could have used negative 10, negative 100, negative 1,000, and the same thing would have happened. Okay? So that's actually a very nice feature, because what that does is it allows us to find limits very quickly. So let me show you how that works. We're given a function, 5x cubed minus 3x squared plus 10x. And we're told that we're going to take that function, in part A anyway, and divide it by x squared. So we're literally going to write that in just like that for starters. 5x cubed minus 3x squared plus 10x divided by x squared. And what we want to do is the same thing we did in the previous lesson when you guys voted, if you will, to reduce the fraction to start with before we did derivatives. We want to make this fraction simpler, and you can do that because the fraction's denominator is one term. There's no addition and subtraction. So I can take each piece of the numerator and divide it by x squared. So this is 5x cubed divided by x squared, and 3x squared divided by x squared, and 10x divided by x squared. Okay, I haven't done any calculus so far. I haven't even talked about limits. This is just algebra stuff. Is this okay? Right? I can reduce this now, right? So 5x cubed divided by x squared is 5x. And 3x squared divided by x squared is 3. Negative 3, because there was a negative. And the 10x over x squared, I don't want to bring it up like I did when I was looking for derivatives, but I can reduce it. So I can write this as 10 over x. Okay, all good? Yeah, 10x, that's right. All right, so here's what we're doing. We're actually supposed to be finding the limit as x goes to infinity of the quantity that we started with. So in particular, we're supposed to be finding that of the 5x cubed. Whoops, I wanted to move that. Copy. Paste. I want the limit of all of that as x goes to infinity. And that's correct, but it's much easier to take the limit as x goes to infinity of the reduced version that I did. Right, the thing I found in all that algebra simplification, this piece. You don't have to write both these steps out as you're working on it, by the way. I'm fine with you just jumping to the second line here. That's fine. But that's what we're doing. We're trying to take the limit of what we were given. We've manipulated it some into a friendlier form. And according to this theorem that we had over here, right, this limits at infinity business, this part at the end is 0. I need a thicker pen again. This is 0 because it's in the right form. It's a constant over x to some value. It's 1. It's not a very exciting one. But according to what we saw before, that's 0. This piece, we've seen that before as well. When we take the limit of a constant, it's the same as it already was. Doesn't change. What happens, though, if I try to put infinity into 5x? I mean, I let x get infinitely large. You get infinity, right? If I take something getting infinitely large and I multiply it by 5, it's infinitely large. Somewhat, you could say faster, right? But it's infinite as well. So this piece is infinite. So I have something that's infinite minus 3 plus 0. And if I combine all those together, what do I get? Infinity. So this is infinite. And we'll verify this with our calculator too, just so that you can see it did what you expected it to do before we did any simplification. So I'm going to put in the 5x cubed minus 3x squared plus 10x, and it will divide by x squared. And we're just going to do our standard windows, so zoom 6. When I say that, it might not even show it on the screen. Yeah, it doesn't. Okay, so I need to zoom out differently. What are my values? I'm going to hit zoom 0, which is a zoom fit function. We'll see if that will work. I don't know if it will or not. Well, that's not bad. Well, it's the same rational kind of function I saw before, right? And what happens over here as x goes to infinity? It's going to infinity. Yeah? So this is verification that this makes sense from what we've done. Okay, we're going to manipulate with this same 5x cubed, etc. function next time and finish 3, 5 then.